and ladies and gentlemen. Good afternoon and welcome to the Korea AI Summit 2025. And my name is Dongbo Min, a professor at Ewha Women's University. And it is great honor to serve the chair for this afternoon program. Okay, now we will resume with the next presentation. The Professor Byung-Tak Jang from Seoul National University will deliver a talk, and the title is Toward a Universal Learning Machine, Grounding Vision, Language, and Action in the Real World. So please welcome him with a big round of applause.
Does it work? Yeah, thank you very much. I'm Byung-Tak Jang from Seoul National University. I thought this is the opportunity to present our projects. So basically, I prepared the slides as a project result report. The title of our group project is actually Fully Autonomous Learning Machine that continuously learns in the real world environment, which is we actually call the universal learning machines. So the AI developed so fast based on the data-driven approach, and to grow continuously the intelligence of the agents, actually should be able to learn continuously, lifelong learning, continuous learning. So the aim of the project was to build the universal learning machine that learns continuously in a real world, in a real life, and in real time. So to do that, actually, we have about 15 researchers together in the AI Hub Innovation Project. And we did a lot of basic research, actually. But today, I will sample two of them, their results, to share with you. So basically, actually, it should be transformed from machine learning to learning machines. That was the idea. The learning machine will be embodied and will have sensors and actuators. And having embodiment is fundamentally important in machine learning point of view. For example, in current machine learning approach, if I have a body and then a sensor and actuator, I can try this to lift the table. It doesn't work. So I know that this table is fixed or I cannot lift the table. So without any other help from teachers or outside information, I can myself learn myself. That's a fundamentally different approach to machine learning. So there's an environment and the agent. So they interact with each other, and actually the action is changing the environment, and that it also has the perception part, sensors, so it can know that the outcome of the action is correct or not. So by checking that, it can learn itself. That's the basically importance of the embodied agent. So recently, actually, there is a much direction to the physical AI or embodied AI. And basically, two different frameworks are being pursued, I think. One is the modular perception control approach, as you see here. Basically, I will show you in the next slide a little bit more. Another approach is the VLA style of models. So in the first approach, we separate actually the physical part from the mental or upper part. So basically, given the visual perception, and the language instruction, pick up the blue cup, for example, and the vision language grounding. Usually, this is done by the VLM, vision language models. And then usually that generates that kind of output. Basically, coordinates of the objects to pick up. That's X, Y, Z coordinates. What's wrong? Yeah. And then that's the gripper actually. So basically it can generate the target position, and then the additionally the motion planning is executed, and the robotic arm, for example, can lift or pick up the real objects. So it's it in two stages. That is done in two stages. So one, first stage, and then the physical part, execution part is additionally done. But in a more foundation model style of approach, the VLA approach is recently explored by many groups. And basically perception language is given, and then the final end effector outputs are generated. Like it's a generative model as well. Here the generation is a sequence of actions instead of a sequence of words, for example, LLM, in contrast to the LLM, but the idea is basically similar. So the function given perception and language, it generates actions. Here actually the generated output is the end effector positions and orientation, three position, X, Y, Z position, and the orientation of X, Y, Z, and the gripper is open or closed. So by learning the whole vision language action process, actually we can build a large physical large physical kind of AI model. So in our approach, actually, okay, maybe I think I will skip the first part. My colleague Frank Park actually have worked on more robotics side of this general project. They presented I will maybe skip the past. They have been working on articulated object recognition problems, like the articulated objects are the objects with the movable parts. And to recognize that part is important, and they proposed the Gaussian splatting method called the screw splat. And basically, it doesn't need much prior knowledge. And by sampling, basically, in the space and optimizing, they could correctly recognize the articulated joints, as you see here. So I will go very fast here because that's the preliminary part of the physical intelligence. So once you recognize the articulated parts, of course, you can use the robot to do something, like close the laptop or open the laptop. So once you recognize which part is the articulated axis. Oh, okay. In this work, actually, we didn't have the perception action cycle, which I called to be a universal learning machine. You need to combine or cycle the perception part and action part in a cycle. They learn from, so action learns from perception, the perception learns from action, and the cycle goes on to be continuously learning and getting experiences. Here it's missing, but still very excellent work in vision and the robotics problem, I think. Going further now, that's the topic maybe for today. We have been presenting one large language model called the CLIP art. CLIP, as you know, the vision language model, pre-trained vision language model. Basically, we extended it to robotics problem, physical AI, by generating, using the vision language model as a perception part, and then using that to generate robotic actions. So one big idea in this model is that we use language as a training method. We train the embodied agent by language. Language is just usually used for learning knowledge of world knowledge, but we use language to train. It's a basically teleoperation by language. We teach the robot by language, and that's the new idea here. So basically, we learn language conditions, robotic policies from natural language supervision. Let me briefly show you how we work. Basically, the VLA, current VLA, usually gets, as I said already, vision input as well as language instruction. For example, pick up the blue cup. And then it generates the final code actions. Actually, that's the delta values of x, y, z, and the orientation. But to do that, this numerical execution generation part, it's hard to be generalized. So the idea of us is to, instead of these numerical vector to learn, we learn actually a little bit abstract linguistic representations. So that's called the language-based motion primitives. We defined a large number of motion primitives, around 900, basically. And then basically the learning is in terms of these linguistic representations. The good thing about this is that it can generalize very well because it's not learning the numerical part directly, but in the representational part. Of course, we should generate the motor control, but that is coming later. Basically, we generate the abstract motion primitive to do, and then that is executed later. So, and how we teach the robot, the agent, embodied agent. Basically, that's the prompt. Pour the dog food in the bowl, and then image. And then actually using LLM, it generates a sequence of primitive actions like this. Or actually at the training phase, humans give instructions in these primitive actions, and actually it generates the sequences. So for training, actually humans generated the actions primitives. Once we collected that whole data set and learn, it can later automatically. So we use LLM as a help. Also, the humans give instructions in detailed and some primitive, a little bit detailed instructions, and that is learned. So this is the general architecture for that. So so we have instruction part and the image part. The typical vision language model, right? Like this is a clip style. And then we defined the primitive actions, and we use that in supervision. So the basic approach is imitation learning from humans and using the contrastive learning. So maybe the next step, yeah, right. And then this is the context actually, and this is the action. Basically, we compute the similarities between the primitive actions and the context vectors. Context consists of vision and language as a multimodal model. So context and primitive actions, the similarity is calculated and optimized by this way. This is a contrastive imitation learning. Imitation learning because it comes from the human execution, and then the loss function of the contrastive imitation learning is defined this way. Basically, the SSIJ is the similarity between CI and GJ, basically for all mini batches of a size M. So the idea is that given the context later on, the primitive actions as a library will be executed. The most probable primitive action will be executed given this context later on, once it's learned like this. So once learned, there's a closed loop now. If it given the context, current context, it chooses the most probable motion primitives, one of them, and then chosen the action is executed, and then the next sequence of action generation will be repeated. So the idea here is to define the motion primitives. And you see here a little bit quantitative, a little bit discretized, but very concrete motion commands are defined actually, and by learning, it chooses the most probable appropriate actions in terms of the context, right? So here are some results, experimental results. Okay. For here, the common task and novel task. Common task here means we used as the pre-training data, X embodiment, open X embodiment data. It's about 2.4 million episodes or something, which have been also used maybe the open VLA model as well. That's the baseline here to compare. And those common tasks, for common tasks, also we used for our robotic tasks, we used novel tasks and collected the data like these in using our arms. Basically, we compared the results. The clip RT, our proposed model, basically outperforms the open VLA in average success rate by 24% on novel manipulation tasks. On common tasks was more similar. I hope you can see that. Those are the VLA, the gray, and the blue is the clip RT. Very similar on common tasks, but in novel tasks, the difference is more contrasting. The clip RT outperforms about 24% in average. So why? Some assumptions we made hypothesize that maybe, as I already said, the linguistic action primitives it's a better generalizable representation. So to verify that hypothesis, actually we experimented some additional work. For example, in this experiment, so episode was, in this case, only presented once, or 5 times, or 10 times. That means if you present many demonstrations, then all the different methods converge to do very well. But when the demonstration number is small, meaning that few shots, and the open clip RT generalized, you see the clip RT generalized is better, especially on a small number of demonstrations, meaning that it generalizes faster. Another experiment we have done was maybe the generalization can or the knowledge transfers to multitasks. So to do that, we trained the open VLA and ClipRT in a single task and the performance. And then we also trained the same models for multiple tasks. So by single to multiple, the generalization performance in open VLA was about 3%, while in ClipRT, as we train more tasks, the generalization performance improves more than the open VLA. We can see that, meaning that you additionally train the model on different tasks. As you increase the number of tasks, it could generalize better. Another final part, actually, of the advantage of this method is we can use humans for additional training. So when it performs, while it performs, and the humans can intervene, meaning that humans can correct the actions of the trained robot, and then like 2 intervention and 4 intervention. If you intervene 4 times, all the models do perfectly. But as you see, the number of intervention is 2 times, then the ClipRT improves better than or faster than the open VLA, the traditional model. We can also use the LLM as a guide for the learning process. So, for example, you give the instruction and image and execute, then the primitive actions were generated by ClipRT, already trained. But you can also ask that to GPT, and GPT corrects that. Maybe this primitive instruction is not good, and this is good. So the GPT knowledge can correct some proposed preliminary primitive actions. So that means that GPT can guide the learning process. So we can utilize the LLM to learn continuously, as well as the humans. Okay, I think I should stop here. Thank you very much. Yeah.
Right, so thank you for your wonderful talk. And any question from audience? Okay. Okay, so let me ask you the one question. Actually, I noticed that there is as you know, the NVIDIA released some foundation models for the VLA, last April. Then in this technical report, NVIDIA released, they noticed that, they say, okay, we train the deep learning model, vision language action model using a lot of the GPU, more than 1,000. So in such a case, same problem is happening once again, just like what happened in the LLM. So I just want to ask you, what is your insight about some paths we must pursue from the academia perspective, precisely speaking, the Korean academia? Okay, do you have any insight about these things? So what can you do with you less, very limited amount of the computing power in academia once again?
Right, in the physical AI, in that side, so we need maybe much more data than the large language models, but we still miss a lot. I think in that sense, this is just a start. So additional computing power might be a big problem, as well as the big data. So it's exciting that we should do the LLM style of work, maybe again. Maybe not the same way. We need more ideas, I think. Yeah.
Yeah. Thank you for your wonderful talk. And please give a big round of Rouse once again to
Thank you very much. Thank you.
Myung-guk Yoon from Ewha Wons University will deliver talk, and the title is "Can Unified Virtual Memory Replace the Copy Then Execute Paradigm in AI Inference and Training?" Please welcome him with a big round of applause.
Thanks for the introductions. Okay, my name is Myung-kuk Yoon from Ewha Wons University. I'm going to talk about the idea of the unified virtual memory. Basically, my research interesting is how make the computing performance faster. So this day AI is the important matter. So my major goal is to try to finish how the execution is faster. But rather than that, today I'm going to talk about giving you the idea of giving you a potential to training the models that's exceeding the memory size on the GPUs. So you all know that the training, they require a lot of data, and then we pay a lot of money to buy the better GPU. Basically, the better GPU, they do have a higher memories, which means more space to put on it. So if you look at this graph, LLM, training the LLM become like they have a lot of weight, and then you have to store a lot of data in the memory, in the GPU memory. However, the memory size on the GPU has very limited. The largest one is around about 140 gigabyte. That's a really, really tiny compared to the model size that you have these days. So basically, I just picked the one of one, GPT-3. They do have 175 billions of parameters. So simply just calculating in order to training that data, you require to have 350 gigabyte of the memory. Just simply that I assume that you have 800 GPU. You require to have at least 5 GPUs. Without that, you cannot even try to training. So while buying the new device with the higher memory, larger memory space, they do require a lot of money. Just simply compare that you have 6,000, A6000, they use a lot, and then A5000, two different models. Their performance gap is around 50% faster, but they have twice higher memory spaces. So basically, you're paying more money to buying the memory spaces. Have you ever tried to put the memory in the server systems? Just memory, one slot that has in the 64 gigabyte does not cost more than $500. Sometimes they go up more, but these days around $500. Compared to that, GPU memory is really, really expensive, and then you pay a lot of money for the spaces. Most of the training that you've done in the PyTorches and things like tensor cores, they do depending on copy, then executing CTE models. Basically, CTE models, program, have to move the data from CPU to GPU, GPU to CPUs. That's all depending on how you are programming. So basically, they are done in this way. And the unified virtual memory is basically considered that there's unlimited of the space of the GPU memory. They're using the CPU memory to storing the more informations. So basically, in order to support the UVM, we have to remove the copy and executing paradigm. So instead of the programmer copying the data from the CPU to the GPU, GPU to the CPU, they require the driver, UVM driver. Basically, like the OS, they are just managing the pages. The NVIDIA driver, they support the demanding paging techniques. Basically, when you need it, you copying. You don't need it, you don't copy the data. So programmers do not need to know whether they want the data or not. Just it's done by automatically through the drivers. So let's slightly talk about how you guys are training in the computer system. They do have 4 different popular training techniques, basically parallelisms. They do have a data parallelism, and they do have a model parallelisms. In case of the data parallelism, the most popular is DDPs. Basically, they copying all the models into the 2 different GPU, 3 different GPU, depending on how many devices you have. In case of zeros, they have a 0, 1 and 0, 2, 0, 3s. Depending on the levels, they do dividing the different parameter into the different devices. I will go over more details. And model parallelism, they do have 2 different pipeline parallelism and tensor parallelism. Pipeline parallelism is basically dividing the layers, and then they sending the different layer to the different GPUs that they executing in the parallels. Tensor parallelism is basically dividing the task, the tensor. Basically, in the AI application, many of they are depending on the GMM operations, the operations. So they dividing that large GMM into the sub GMM, and then they sending into the different GPUs. So Basically, DDP, it's easiest way to using it because they just copying the all the weight and then all the parameters into the just multiple different GPUs. And next one is basically zeros. Depending on 1, 2, 3, they dividing the different part. So if you look at the 0, 1, they're dividing the optimizer. 0, 2, they dividing the gradient. And then 0, 3, they dividing entire motors into the number of the GPUs. And next one is pipeline parallelism, basically dividing the layers. So depending on how many GPU you have and how many layers you do have, they are dividing the entire task. And lastly, tensor is they dividing the entire smaller GMM into the sub GMM, and then they spread out into the GPUs. Simply, let's assume that I have the two different type of the GPU, A6000, and then you have a 4 A6000, and then you have two A6000s. Let's look at the, you have a GPT and then 1.5 billions. There's none of them that can be trained on their systems because they don't have enough memory to training. How do we solve this one? As I said, if you're using the unified virtual memories, they do using the CPU memories. So what it happens is you are able to training all of them. But you have to pay the prices. They are slower, but they can try to training. So, well, in terms of industry, I'm not sure whether this is good way to training, but in the schools, I think it's a good way to training the data because it's expensive to buy GPU. You don't have enough GPU, but you would like to see the result of the higher motors, like more like weight. You can using the unified virtual memory to training, at least try, and then you can see the result. However, the problem comes with the performances. So depending on the parallelisms and then depending on how you are optimizing that system, you will have a different result. So what we have done, we basically compared the 4 different parallelisms onto the UVM and then how you have to handle each data in order to see the best performance on your computer systems. So first thing is basically you have to using the finer grain granularities to training the data. So we start from the DDPs, and then we start from the 0, and then we start from PP and TPs. As you move on, basically DDP, they have the same weight onto the multiple GPUs. However, in the TPs, their size is the smallest one. So in order to using the multi-GPUs, when you are training, you have to updating the weight and then you have to calculating the gradient and things like that. If you're separating the entire weight into two different GPU, they have to communicate a lot larger chunk of the data. However, the frequency will be a lot lower. However, if you move on to the TPs, every tensor is divided into the sub-tensors. So what it happens is you are communicating a lot more frequently. However, the size that you are communicating between that GPU is a lot smaller. So based on how you are communicating is depending on how you are training. You can using the all reduced scatters and things like that, but their communication size is really depending on the size of the parallelisms. So in the worst cases, such as DDP, they do require only one-time communication at the backward propagations. However, their size is a lot larger. If you're using the TPs, they communicating each layers, but their frequency become a lot larger. So they have to communicate at least 48 times. However, their size is smaller. So we basically try to using the order algorithm and try to look at the performance of the algorithm. So once again, if you're using the GPT 13 billions, you are not able to train the data on A6000 using the 4 GPUs, but we can do it using the UVM. If you're using the different parallelism, as the size gets smaller and then the communication frequency become larger, their performance is a lot better than any other algorithms. Then the second one is basically, so I've seen as a result, dividing the smaller chunk and then you communicate more frequently will not, most of cases they show the good performances, but in some cases they do have a different result. And then we look at the result, and the main reason is because of the communication frequencies. So if you can overlap the performance, overlap the operation between the multiple GPUs, they can hide in some of the stores, but if you don't have enough computation, they might not be able to see the good performance improvement. So whenever you do, you have to consider the number of the frequencies that you are communicating between the GPUs. So you have to be carefully using the multi-GPU in order to see the good performance and then in order to get the best result from the multiple GPUs. Just move on to the third one. So, well, as you can see, the DDP and TP and PP and different parallelisms, their memory requirement is different. Because in case of the DDP, they tend to copying the order weight into the multiple GPUs. But if you look at the TPs, they require to have the sub-tensors in each GPUs. So what it means, there's memories, even if you're using the UVM, the required memory size is different depending on the parallelisms. Whereas CPU, they do also have the limitation of the memory. So you are not able to using the unlimited memory spaces. So if you look at this requirement, the memory requirement of the GPUs, so from the end-to-end training memory consumptions, as you have the lower, like dividing more smaller tasks, they do using the less memories compared to the DDPs and PPs. DDP, PP, they do have a lot of data they have put it into the multiple GPUs. So what I mean, you have to consider the memory sizes as well in the CPU, even if you're using the UVMs. So another reason is important thing is as you using the smaller chunk, finer grain of the memory sizes, what it happen is the GPU tend to have some of the empty spaces. What I mean, you can bring the data into that empty spaces. If you're using the coarse grain data, what it happen, in order to bring the new data, you have to change in the entire coarse grain data size from the GPU to the CPU, CPU to the GPU. This increasing the number of the page fault, basically how many times you are bringing the data, how many times you are evicting the data. This is basically showing the number of page fault, how many times you have to migrating the data into the GPU and then evicting the data into the CPUs. So lastly, important thing is the scalabilities. So you buying the more GPU, not just for the memory, just to get the higher performances. Then in order to using the different parallelism, and then you buying the more GPUs, you like to see the performance improvement, right? So basically same ideas. So they tend to, you have the DDPs, they buying the more GPU doesn't really increasing the performances because they are basically copying all the data into the multiple GPUs. So what I'm going to show you here is as you buying the more GPUs, DDPs are basically copying all the data into all the same memory spaces. However, if you look at the 0 and PPs and TPs, they do actually dividing the sum of the job into the multiple GPUs. So what it happened is if you increasing the number of GPU, we compared the GPU 2 with the number of the GPUs equal to 2 with the GPU 4. What it happened is if you using the larger chunk of the data to training, such as the DDP and PP, as you put in more GPU, does not showing you the higher performances. What it happened is they are losing the performances. You bought the more GPUs, but you are losing the performances. However, if you're using the tensor parallelism and 0-3s, they tend to have a smaller chunk of the data. So what it happened is they are showing the better performance. You are paying money to gaining the performances as more spaces. So on today's talk, I basically tried to give you some ideas. Well, once again, the UVM was there about 10 years, and then no one was really interested in that UVM drivers and things like that. The main reason was, I think, because of there wasn't any application that exceeding the GPU memories. But these days, memory is expensive, especially GPU memory is expensive. So, well, in the industry, they do have a capability to buying the thousands of the GPU, but in the schools, that's limited, the resources. So in terms of looking in the different application, I think using the unified virtual memory to training the models, I think you have a more potential to look at a different algorithm, and then I think they will give you the good result to learning in the schools. However, you have to always think about making the parallelism. So make it smaller, make it divided into the multiple GPUs, then you will see the good result, and then you will see the fairly good performances. And another important thing is these days, performance is also important, but these days we are actually considering about the token per dollars, right? So let's assume that you are borrowing the GPU from the AWSs and the different cloud system, and then we look at the prices, and then you're just paying more GPU just to using the CTE models. They do spending more money per tokens compared to using the UVM. So I think this is end of my talk. And then if you have any question, feel free to ask. And then this is it thanks for listening.
Okay, so we have a lot of more minutes. So if you have any question, please raise your hand. Okay, so let me ask you the few number of questions. Actually, I'm not so familiar with this the hardware, so I'm working on the algorithm. So I just want to ask you the very simple basic question. So, I mean, in case of using the virtual, I mean, unified virtual memory, does it make any problem in terms of the power consumption?
Well, in terms of power consumption, well, I have to measure the powers, but the GPU, they use more power than the data that actually copying from the, I think,
So you're
CPU.
copying some of the data from the GPU to CPU or inversely. So in such a case, does it make any big problem about some consumption
even
of
if you're
power?
using the CTE models, you have to copy the data from CPU to GPUs. That's depending on the programmer. If programs are doing really, really good job, they probably copying the data they only needed. But if they are not done well, then I think they probably going to use some chunk of the data that never going to be used on the GPUs. Then I think they spend more power than the simply just using it as. I think it's really depending on how you're optimizing. But I think if it's well optimized, I think a city model is the bestest one that you can use. But well, as I think it's a prices, GPU prices keep going up, and then it's hard to getting that devices. Then I think this UVM can open the door for the AI, the developers who look at it, at least the training the data, and then they can see the result, even if they don't have enough GPUs. Yeah.
So do you have any question? Okay, so if you don't have any question, please give a big round of the applause to the speaker. Tae Kim from Gyeonggi University will deliver a talk, and the title is Collaborative Intelligence Enhancing the Human AI Trust Through the Model Interpretation. Please welcome him with a big round of applause.
All right, thanks a lot for the introduction. I'm currently working at Gyeonggi University, and we were consortium number 9 in AI Innovation Hub project. And our title of our project was Collaborative Intelligence. It has a lot of different meaning in AI. For example, many of our publications were for the decentralized learning, that is federated learning. But in the one side, our team also made research effort to improve human AI trust for collaboration of human and AI. So today I want to introduce our recent work on this topic. As many of you already know, human AI collaboration is growing. So yeah, AI can support decisions in medicine, finance, or manufacturing. This a hybrid intelligence system where human and AI are collaborating together to make a prediction, outperform human-only systems or AI-only systems. Now it's more important because we can see many research and development between human and robotics. So for this human AI collaboration, one of the important next step is trustworthy. So interpretability is one of the important aspects for building the trust between human and AI. So users can trust AI only when they can understand how decisions are made. So transparent reasoning will make safe deployment of AI systems in mission critical domains like medicine. So explainability bridges the gap between AI decisions and humans' expectation. So as you can see in the right figure, current AI or previous AI does not provide an answer when users make a question like why. So this is the fundamental limitation of previous AI that is black box nature. So users cannot understand why the model made a particular decision. This kind of lack of transparency makes it skepticism, hesitation, and even misuse of AI systems. So model reasoning is often misaligned with human expectation, and this makes uncertainty. So we need one more step from black box AI to explainable AI. It will make hidden model reasoning more visible and understandable. This is very important for real-world users of AI, and it could help clinicians access reliability and risk in medical side. Also, it could support human AI decision making in mission critical domains. So in the below example, we can see that explainable AI can provide explanation for the decision with a keyword or, human level concept explanation. So in the AI research domain, there are many research efforts to provide explanation to the AI engineers and users. So pitch attribution is one of the important research domain where researchers try to identify which feature, which part of input most influence the model decision. So it could help humans understand what factors matter most. So that means it could explain from individual prediction to the model behavior. So below figure is the representative example of pitch attribution that is GradCam. So it highlights which pixel in chest X-ray image makes most influence the model decision. This kind of pitch attribution can be used for the model, evaluating model. So for example, as you can see here, so this kind of pitch attribution map can be used to numerically measure how interpretable the model is. This was the some of the research trend at the XAI when we began this project. So at the time, we also have interest in this topic, and we want to make a more new algorithm, more novel algorithm that can help humans and users. So at the time, our motivation is that traditional pitch attribution method, like a GradCam or gradient-based explanation, often highlight very broad area of images. That means it is difficult to identify which specific input features actually influence the prediction. So our method, our proposal was, then let's make a new method to generate more fine-grained and feature-level explanations by identifying which precise input component carry predictive information for model. So this was presented 4 years ago. But yeah, after this publication, we have found a major limitation of pitch attribution. That is, the method for measuring the attribution of each feature can only answer for the question like, how much did each feature contribute? That means its output is just low semantic meaning, so it could not provide why this spot. And there is no insight into what concepts the model has actually learned. So we thought that this kind of technology is useful for AI engineers, but it is not enough for real-world decision makers, real-world users of AI. So we thought that what real users need. So real-world users need what concepts the model detected, and also where it appears in the image or video, also why it influenced the final decision. So they need explanations represented in human understandable concept, not just low heat maps or gradient. So we went back to the another domain of XAI, that is picture visualization. So it is a research domain that people try to visualize what pictures neuron detect. So that means they try to find out what kind of images or what kind of patterns maximize the neuron activation, as you can see in the right formulation. So as a result, it can reveal which visual patterns or texture a neuron respond to. That is a learned picture. So this visualization can provide insight into the model's internal feature detector. And also it could help whether model learns meaningful patterns or it's just a spurious patterns. So for example, this is not a new study. So 7 years ago, people tried to understand what these patterns, what these images. So in the medical side, they try to investigate and understand what they mean. So in order to understand this, they collect medical expert, and did the user survey, whether collected or representative images has some meaningful patterns or not. So interestingly, when the model was just classified as malignant cancer or benign, internal representations, internal neurons are aligned with real-world meaningful medical concept. So some neurons looks like very highly semantic coherence with this medical keyword. We could formulate this kind of understanding neuron in this way, more general way. So when we have a model, neural model, as you can see here, yeah, it could be image classifier or any kind of model. There will be a lot of neurons nowadays, millions or billions of neurons. We can select one of the neuron that we want to understand, and then we could find out what kind of input maximize this neuron. So this is the example of representative image selection. So we can choose, for example, if we have a training samples, training data, we could choose the top activating images for this specific neuron. And then concept annotator can interpret what they mean. So human can annotate concept, as we can see in previous slide. But nowadays, we can do this with vision language models or multimodal large language models. Of course, for this, we need to define some of the list of keywords that is used for interacting and explaining the model. So that is a concept set. So last year, we introduced one of the framework by using this. So we bring the vision language model, that is CLIP. And from the representative images, we measure the similarity between these image features from vision language model. And also we collect a concept set that is used to understand these neurons. So we extract text pictures from this text and find out which text mostly represent this set of images. So in this case, this seafood keyword achieves the highest similarity compared to this set of images. So in this way, we can annotate neuron as a seafood detector. So this can be applied to different layer of models, as you can see, and also different architectures like a transformer. Of course, we further introduce locating this concept. So we are trying to identify some spatial locations in the input image where the neuron concept is activated. And also it can be extended to understand failure cases of model. Right after this presentation, our team thought about which application will be most important, or I mean, which application we should apply and verify this. So that was the medical domain. So as we can see in the very beginning of my presentation, previous AI just provide a prediction, but it cannot explain in terms of human level keyword. So we did same things. So we for the model that classify these input images, we select a neuron and we can collect what kind of images highly activate this neuron. And also we collect a concept set that is used to understand what features this neuron can detect. So for this purpose, we collect a keyword from medical report. By using this, now it is possible to explain the model decision, like there is an abnormal in this chest X-ray image because the highest contributing neuron detect ectolysis. Of course, at the time, we also used the neuron contribution measure. After that, this year, we further extend this to the surgical video understanding domain. So this is more challenging because the input is the video, and each frame, it makes a dense predictions of what the surgical step is. So we interpret each neuron in surgical face recognition model as a human understanding of surgical concept. At the time, of course, we bring the vision language model that is trained on surgical video domain. And also we collect what kind of keyword and a phrase or word will be meaningful for the real world users. So, and then we did and show that this can be used to explain model decision. So, for example, from this video, this frame was classified as gallbladder packing phase because the toughest contributing neuron was to extract gallbladder into the bag. So in this way, it was possible to explain model decision from what features neuron detect and which neuron makes a highest contribution for this model prediction. This kind of study was regarding when we have a good model, good trained model, we were trying to understand what is the some concept that this individual neuron detect, and also by using this individual concept, we are trying to explain model. But now the next step we are trying to do is this kind of concept that is some common unit that we can interact between human and AI. This can be used to design more interpretable model. So this is a collaborative work with Professor Jinu Che in Kyung University, and we will make a presentation on next year's in Europe's. So traditional video models rely on entangled spatial temporal features, and this makes it's very difficult to understand what is the reason for this prediction. So in order to improve the explainability, we introduce a new framework where video action predictions are expressed as combination of human interpretable, compositional, and separable concepts. So in this domain, we define for action recognition, it is important to define motion dynamic concepts and also object concepts and scene concepts. By combining contribution of its neurons, its concepts here, our model can make a more interpretable prediction for a given image, given video. Okay, today I introduced some of our recent work on collaborative intelligence. I think future of AI is collaborative. So AI must work with humans, not replace them. So explainability makes AI listening visible, and it makes a trustworthy collaboration. So concept-based explanations that I introduced today will connect model behavior and human understanding. Of course, it will be important to build AI systems that are not only more capable, but also more understandable and reliable. It is important to align model with human value and expectation. And also, it will be important to empower humans and AI to learn, correct, and improve together through interactive collaboration. So collaborative intelligence starts with trust, and trust starts with understanding. Thank you.
Right. So thank you for your great talk. So any question from audience? Yeah. Okay. So let me start with the small question. So I mean, I'm not so familiar with the DEEG part, but let me ask you the basic question. So it is very impressive to extend the DEEG explainability into the medical domain. But I'm just wondering, how do you quantify? How can you quantify the explainable capability, especially for medical domain? Yeah.
Yeah, this is a very important question.
Yeah.
Of course, it is difficult for me, but this is a next step that we should evaluate. Currently, we evaluate our method in a systematical way. For example, we define proxy task, whether we made a concept annotation and we evaluate whether this kind of concept annotation is faithful and meaningful in a systematic way. But next step will be this kind of explanation is really meaningful for the real world users like medical doctors or surgeons. This will be important step.
Yeah, this is why I'm asking this question. I mean, the most important part is engagement by the medical doctor. So how many medical doctor must be engaged, and then if possible, I mean, how they are engaged? I mean, in which way? Yeah, that's my question.
Yeah, this is a good point. So there will be multiple level of evaluation, I think. In the very beginning, we started, actually in this project, we start from one surgeon in the hospital, and we discuss about what kind of concept, what kind of keyword is meaningful or not. So in this way, we can verify our explanation is meaningful for them, the real world users. And then I think the next step is whether this kind of explanation is really meaningful for them, I mean, for the community, for surgeons community, for example, and then whether this can be really improve their effectiveness when they collaborate with AI or robotics. I think this is a future work.
Thank you. So do you have any question? Okay, so if you don't have any question, time is over. So thank you for your wonderful talk, and please give a big round of applause once again. Yeah. Right, so next Professor Hyunjin Park from Seonggyungan University will deliver a talk, and the title is Generative Model with Radio Mix in Medical Imaging. Please welcome him with a big round of applause.
Hello, everyone. My name is Hyunjin Park. It's my pleasure to give presentation in this conference. The title of my presentation is Generative Models with Radiomics in Medical Imaging. I know that you don't know radiomics, so I will explain them in detail. Currently, I'm leading the AI Hub project at Seonggyungan University. Our goal is to develop AI methods specifically for medicine. Here, we are tracking 3 technical challenges. To tackle explainability concerns, we are developing responsible AI. To allow expert intervention, we develop interactive AI. To handle partial and imbalanced data, we are developing robust AI. We have an interdisciplinary makeup of teams. We have engineering faculty and medical doctors. The engineering faculty come from Seongyungan University and other collaboration sites. Physician faculty come from Samsung Medical Center, which is the affiliated hospital of Seongyungan University. Okay, this is the content of the presentation. I will introduce two topics. The first one is generative radiomics, where I will introduce two conference papers from my group. The second topic is retrieval radiomics built on the first technology. Again, this is a conference paper. Okay, radiomics. Radiomics is the commonly occurring theme in this presentation. The terminology is a combination of radiology, medical imaging, with suffix omics. So we are basically analyzing radiology data in an omics fashion. Since it's an omics analysis, it involves high-dimensional quantitative imaging features. It typically includes 60 to 100 standardized features. The features are categorized into shape, size, and texture categories. The features reflect tumor phenotype and microenvironment in medical imaging data. Most importantly, standardized framework. It is a standardized framework to analyze various targets and various organs. They are fully expert certified, hence explainable. So they can act as an external conditioning variables in the generative framework. In a typical radiomics analysis, so you define mathematical, you have various mathematical methods to analyze texture, and many of the most famous one is the halo-rect texture feature. I don't know how to point, so. This is the first topic, the first top generative radiomics. So I will introduce the recent paper from my group. It appeared in MICAI 2024. The title is Radiomics Film Mammo, Synthetic Mammogram Mass Manipulation with Radiomics Features. So we use conditioning to generate breast X-ray. The research motivation is, can we generate tumors with desired attributes? So the left-hand side is your typical brain MRI with real tumor in a red bounding box. We would like to generate synthetic brain MRI with various tumor locations, sizes, shape, and texture. Okay, I can point now. In a typical medical image analysis framework, we start with the medical imaging and a tumor ROI, and we extract many radiomics features. And the radiome features are used as the input to machine learning models to explain clinical outcomes. So the radiome features are input to a machine learning model. In our work, we reverse the flow of the analysis. We start from the radiomics features and try to generate medical imaging that matches the radiomics condition. Okay, this is the method section. The backbone is a stable diffusion with the denoising unit. And input is a mask image, tumor mask image, and the other lateral image. The breast mammogram has two parts, left breast and right breast. Only one part contains tumor, so the other part has normal tissue. So we can provide input with normal conditions. And then we also need to provide the tumor conditions through the radiomics features. And the output is the in-painted image reflecting the tumor phenotype. Okay, from the method, we need to enforce some kind of consistency. We try to match the radiomic features from the original image and the radiomic features from the generated image. So we need to confirm whether it works correctly. So we quantified whether the radium feature from the real image and the radium features from the synthetic image match. And we compare different features in terms of different categories, 4 categories, and it seemed to match. The right-hand side is the actual pictures comparing real and synthetic data. In the bounding box, you see tumors. the histograms are visualization of the radiomic features, and they seem to match. This is the results section. So in this particular case, we want to demonstrate the usage of synthetic data. Here we are demonstrating in a downstream task of math section. Baseline refers to using the original real data. 1x is using synthetic data only, and 2x is using both real and synthetic data. As we use more samples, you can see that detection performance improves. This is the results of showing visualizing condition-specific tumor variations based on the left-hand side original input, where the tumor is marked with the red bounding box. We can generate progressively small to progressively large tumors in different locations. And the size was given as the input variable, but as we increase the size, other texture features will stay relatively constant. Okay, that was the first paper. So the first paper was generating a 2D medical imaging. We want to do an extension to 3D. This one appeared in WACB 2025. The title is Tumor Synthesis Conditions on Radiomics. Okay. So why do we need another generation model? Because we use 3D medical imaging more often than the 2D medical imaging. In this case, we demonstrate our method works in abdominal CT and brain MRI. Based on the medical imaging input and tumor ROI, we can change the tumor texture, remove tumor, or change the tumor shape. This is the method section. For controllable 3D tumor generation, we first need to do image compression. Since this is 3D data, we cannot do direct manipulation. So the compression was done through VQGAN. We have a two-step generation process where we first generate the tumor shape, and then we add the tumor texture on the generated shape. This is the shape generator. It is based on the GigaGAN backbone. The input is the shape-based texture, radiomics features, and the output is the tumor binary mask. This is the second generator, texture generator. The backbone is BBDM, Brownian bridge diffusion due to the efficiency. The input is the tumor mask image, and histogram and texture-based radiomic features. Then output is the inpainted tumor image. This is the results of tumor generation for various sizes. So we start with our input, remove tumor, and add a tumor of various different sizes. So small tumor to large tumor. And as shown in the previous example, as we increase the tumor size, other texture features stay relatively constant. The second row is the tumor generation based on texture features. Again, input given here on the leftmost column, erase, and then add tumors with different textures. And the resulting radiomic features are given in the histogram below. This is the result of tumor generation in the brain with various shapes and positions. The tumor shape is given in the different rows in the yellow and pink ROIs. Different tumor positions are given in the whole brain area with the green overlay. We also did a user study to confirm that our generated image and the real image are very similar by two experts. Okay, that was the first topic of generative radiomics. Let's try to move on to the second topic, retrieval radiomics. This one appeared in MICAI 2025, just a few months ago. The title is Radiomics Retrieval, a customizable framework for medical image retrieval using radiomics features. In the existing framework, we can do something like side focus search in a database query. So we'll try to find a tumor with 3 millimeter volume, something like that. And then the retrieval result will give you a tumor image with 3 millimeter in size, but they can occur in various locations. We want to do better than this. So what we want to do is that we want to retrieve with a comprehensive tumor embedding. We want to not only match the tumor size, but other characteristics of the tumor. So the motivation becomes, can we customize the tumor search? We want to, if we query with radiomics embedding, we can retrieve results that reflects the comprehensive radiomics profile. This is the method section. We propose a 3D content-based framework was proposed connecting radiomics features with deep learning embedding at the tumor level. Since we are doing querying, we need to provide anatomical information with positional embedding. There are 2 paths. We extract image features in the image path, and then we can extract radiomic features from the radiomic path. Positional information combined with the imaging feature gives you tumor level embedding. And then we do a contrast learning at tumor image embedding with the tumor radiomics embedding. We perform multi-positive contrastive learning, where at the tumor level, embeddings from the same tumors are positives and other comparisons are termed negatives. This is the result of the location-based evaluation. It measures how well retrieved tumors share the same anatomical location. The metric is a fraction of top K retrieved results. First, comparing different query types. The first query is image and tumor point query, and second query is the 1-point anatomical position embedding. As we provide the direct positional information, 1-point query gives you better results. Within a given query type, adding more training modalities improve performance. This is the result of the radiomics-based evaluation, where we measure how well retrieved tumors share similar radiomics features. The metric is average correlation, again comparing 2 different query types. Query type 1 is image and tumor point query, and query 2 is radiomics feature query. But directly providing the radiomics feature as the query leads to better performance. Similar to the previous result, adding more training modality within the query improves performance. This is the qualitative result of brain tumor. The right-hand side is the existing research. Location-focused query results, diverse results in size, shape, and intensity. We could add another constraint of size constraint, and now we have size match results still occurring in various locations. Our customized radiomics-based query results in image-based query retrieve tumors with similar overall radiomics characteristics. Okay, this is the conclusion slide. Radiomics feature can act as a bridge between data and medicine. We explored how radiomics can make medical AI more explainable, interactive, and robust. For explainability, conditioning generative models on radiomics features enable controllable tumor generation. For interactiveness, radiomics-based retrieval allows flexible search in medical imaging data, helping experts explore tumor by visual similarity and others. For robustness, integrating radiomics with deep learning improves stability, efficiency, especially under limited or imbalanced data conditions. This is a summary statement. Radiomics connects biological meaning with AI, making medical AI explainable, interactive, and robust. Thank you. If you have questions, I'm happy to take.
Thank you for your wonderful talk. So, any question from audience? Okay, so similarly, let me ask you the few number of question. the first. Okay, so you want to generate the training data using the diffusion model in order to address some problem of the insufficient training data, especially for the medical domain. But I'm just wondering, is it trustworthy? I mean, is it enough to the? Is it possible for us to use such a AI generated data for training the deep learning model, especially for the AI? I mean, medical domain. That's my question. Yeah.
That's a very important question. Medical AI, we have a very nice technology. They are not board certified. They are, it is far from being adaptive in the real clinic. Currently, if you generate new images, we can use to train new segmentation models, new registration models, where you can show improvement in numbers. But medical doctors have hard time believing. So what they want is a medical AI that actually improves survival rate, that improves the recurrence rate, something like that. Not just improve in dice numbers, not improve in those metrics. So right now it has limited use, but I think it has good future.
Thank you for your answer. So any question from audience? Okay, then yeah, same let me ask you the one more question. I mean, in the similar line, I mean, so you are generating the training data using the AI model, and then these AI generated training data will be used to train the AI model once again. So this is just some kind of a circulation. And then the research group pointed out this is the problem. So this kind of the circulation, I mean, self-replication will incur the kind of some disaster. So how do you think about this perspective?
I think that there is a possibility. We are reusing the data. So we start with limited data. We make a lot of augmentations, interpolations. In the end, you start from the same data. That's their point of view. But then in medical data, we have very imbalanced data. I think we are very far away from worrying that kind of view. Well, we are never close to 100K, 200K cases. I have all my papers have less than 1,000 cases. Okay. So it's an issue, but I think it's not a serious issue at this point.
All right, so if you have any questions, so thank you for your wonderful talk once again, and please give a big round of applause. Next, Professor Tae-hwan Kim from UNIST will deliver a talk, and title is Learning the Universe, the Deep Learning Approach for Astronomical Image Restoration and Weak Lensing Mass Reconstruction. So please welcome him a big round of applause.
Thank you for introduction. Hello, I'm Tae-hwan Kim from UNIST, Artificial Intelligence Graduate School. And today I will present our research for deep learning approaches for astronomical image restoration and weak lensing mass reconstruction. So our team working on developing AI technology for space observation big data. And it has challenges such as extreme large scale data, as nowadays we have space telescopes, they collect massive amount of data every day. And also it's hard to label data as in its annotation from human experts, so it's quite costly. And finally, data are also noisy because we use some equipment like telescope, and also it's multimodal. So to tackle such challenge, we need to apply AI. And currently we are working on several projects, including satellite image super resolution, and also galaxy classification and detection from image, and also anomaly detection from time series data. And we are actively working with experts in other institutions, including Yonsei University and Seoul National University and Korea Astronomy and Space Science Institute. And today, among our ongoing project, I will present two work. First, galaxy image restoration, and second, weak lensing mass reconstruction of a galaxy cluster. And both of them are published in Astrophysical Journal recently. So first, I will talk about galaxy image restoration. So introduction. So in the photo shown here, so this is from Hubble Extreme Deep Field, released in 2009. And you can see here there are many galaxies and actually about 5,500 galaxies in this single photo. And these galaxies are focus of our research. And as you can see here, the galaxy comes in various size and color. And for distant galaxies appear smaller, and galaxies that are actively forming star appear blue. So in the deep field, we are able to discover a wide variety of galaxies from those of today to those from the early universe. And modern galaxies mostly exhibit similar features such as spiral arms or elliptical shape. But galaxies from early universe often have irregular form. And astronomers have been able to find clue about how galaxies have evolved by studying this deep field. And here I present two images from left Hubble Space Telescope and right now from James Webb Space Telescope. And it shows a cluster of galaxies. And this galaxy cluster actually interact with their environment and evolve. And one thing we can see here is you can see that actually the galaxy behind the cluster appear distort, this green box, due to behind the light caused by cluster mass. Then a surprising fact is that the galaxy within the cluster account only for 1% of total mass. So what makes up the rest? Then this is another galaxy cluster called Abel 2744. And in this image, we show the counters are drawn around the galaxies. And actually, this represent the distribution of a mass. And then astronomers actually believe that because the mass of galaxy is not enough to distort the galaxy behind them. So astronomers believe that their dark matter account for more than 80% of the cluster mass. Then gravitational lensing provides them valuable evidence for existence of such dark matter. And so then we study this deep field image. All right, so let's go back to image restoration of galaxy. So as you all know, now image restoration is the process of recovering a clean and sharp original image, because during the process of capturing image with a camera, it's blurred and also noise can occur. And our image restoration target is deep field galaxy. Specifically, we aim to enhance image of galaxy taken by Hubble Space Telescope to resemble those taken by James Webb Space Telescope. And in this image left, is actually image captured by Hubble Space Telescope. And on the right, then this image from James Webb Space Telescope. Then since JWST has the larger aperture, so there, so we capture the clearer and sharper images. Then our goal is we want to restore the image taken by Hubble Space Telescope to those of James Webb Space Telescope. Right. So that means equivalently, we make the mirror of Hubble Space Telescope the larger and like the mirror of JWST quality. So then we use the AI. So that means we use the learning. Then we need data. So we use a 3 data set. So first, we collected a Hubble Space Telescope data set, but of course we don't have the reconstruct ground truth. We will have to observe Hubble Space Telescope data set. Then we also collected JWST data set, and now it's available. And we collect about 100,000 clean galaxy images from JWST. Then we corrupted these such images by adding convolution and also noise. resemble that of HST. In addition, also we create a synthetic data set called GelSim. So this is no noise because it's synthetic and generated from some theory. Then also we add similar noise to GelSim data set, resemble to HST. Then we utilize the transfer learning. So first we train our registration network on GelSim dataset in supervised way. So that means we have a low quality image and ground truth. Then we train our denoising network on GelSim dataset. And then we fine tune the pre-trained model on JWST dataset. So by doing this way, first the model learn how to recover the original ground truth image. Then next it adjusts to actually real environment. And this is the network we use. We use the Ristomer, the transformer-based image restoration network, consists of encoder and decoder. Then let me talk about experimental result. So here we present the quantitative result in terms of PSNR and SSIM, and for both metric, higher is better. Then we present result train only on GelSim synthetic data, or train only on JWST data, or trained with transfer learning, or no training at all. Then as you can see here, the last row shows no training. Then that means we just measure the metric between low quality image and ground truth. Then as you can see here, our all result actually improve the performance, and especially the transfer learning approach outperform train only on either GelSim dataset or JWST dataset. So it demonstrates effectiveness of our approach. In addition, we also present some qualitative analysis. So here we apply our learned network to low quality image, the left column. And then the middle column is the actual reconstruct image with our approach, and the right column is ground truth. And from top to bottom, there's an increasing level of noise. Then as you can see here, and our approach is we reconstruct the input low quality image and also they cover their structure. Also, we did some quantitative analysis with some morphological parameter of galaxy. So here, the blue dot means between low quality image and ground truth, and red dot means our reconstructed image and ground truth. Then as we check this morphological parameter analysis, then it's more toward the diagonal. It shows the lower RMS error and also stronger Pierce correlation. So it shows we have good reconstruction capability. And for more qualitative result, so also in the left side, we compared our result with multi-epoch approach. So that means we use telescope for longer time to have more exposure, so that we collect more light. Then, as you can see here, then in left side, our reconstruct image from just single exposure, a single epoch, then actually have good reconstruction result. And also right side, because our goal is we want to enhance image quality of taken by Hubble Space Telescope to that of JWST. So we apply the image taken by HST, then as input to our model, then the result in the middle column show then actually enhance the result. And as a future work, so far we assume the fixed the position dependent variation of PSF, but actually this is not practical. So we are currently working on using dependent PSF to further enhance the quality of reconstruction. Second, we are also working on super resolution, so that we increase the resolution of the already observed image to double or actually fourth size, and also with deblurring as well. Right, and also let me talk about our second work, weak ranging mass reconstruction of galaxy clusters. So as described in the beginning of this talk, in this photo, then we can see that actually in the middle, we have strong ranging galaxies. So that means because now density is high enough to generate more than 2 images from a single galaxy. Okay? And also we can see the weak ranging in around the corner. So it does not generate multiple images, but also distort the shape of background galaxies. And observed image is actually a combination of distortion from weak ranging and intrinsic shape noise of galaxies, and also measurement error. And we are working on reconstructing the mass distribution of a galaxy cluster from weak ranging. And this is our process to generate synthetic data, as we need data to train our model. And we use convolutional neural network with 8 convolutional layers. And this is our experimental result. So in left side, we show result of mass reconstruction. So top row is actually ground truth, and second row is our study, and third row and fourth row are from baselines. And as you can see here, overall mass distribution, including large-scale structure, are reconstructed well. And also, right side, I show the result of pixel to pixel comparison. And as you can see here also, this study achieved a better correlation between ground truth and reconstruction than baselines. And as future work, we are currently exploring using other deep learning architecture like GAN and transformer for weak ranging reconstruction. And this is the preliminary result of our ongoing work using GAN architecture. So left is truth and right one is reconstruction result. So it's promising, and we are working on this. So this is end of talk, and thank you for listening. Thank you.
Right. Okay, thank you for your wonderful talk. And any question from audience? All right, so, yeah, we have it.
Yeah, so the question is, you're using PSMR and SSIM?
Yeah, structure similarity. Yeah.
Yeah, so for these images, it has like black background. So I was wondering if the background makes the task a little bit difficult to evaluate. So especially since your one of the results in the first part, the transfer learning
Yep.
did better. So I was wondering, the synthetic data has a very clean background, so maybe that is more advantageous.
Oh, yeah. Thank you for a great question. So we also acknowledge that because if you use the same metric for all, including foreground and background, probably that effect might occur. So we are also working on, for example, different loss. that means we put different weight. For example, it's the brighter region, we use the more focus, and darker region, we have a smaller weight. But also we think computing the metric over the entire region is important, because one of the main goals is we want to reconstruct the structure. So that means we need to denoise the background first, so that we uncover structure. But I think that's a good question. Hopefully answer your question. Yeah, thank you.
Nice. So yeah, there is another question. Yeah, there is another question.
Thank you for the interesting talk. And I'm wondering what's the advantage of enhancing the quality of Hubble images?
I'm sorry, could you
So,
say again?
as far as I understand, the goal of the first part of your talk is enhancing the quality of images taken by the Hubble telescopes
Right.
using, for example, James Webb images.
Yes.
So, I'm sorry, but I couldn't clearly understand what's the advantage of that task. Why do we have to enhance the quality of Hubble images?
Okay. Actually, that's a great question. So since we have already collected large amount of data by Hubble Space Telescope, because it was launched a while ago, like 2 decades ago, if I remember correctly. But JWST just launched last year. So that means can it utilize already taken large amount of data, so that we can utilize, for example, still we need to spare time of JWST for what we want to observe, right? Then we can use this approach to discover the enhance the quality of HSD, so that we can it's like we use the image taken from JWST, like discovering the structure of dark matter in universe.
Then, so as far as I know, I'm not an expert in this field, of course, but as far as I know, using James Webb, we can capture very different images that may contain some interesting information that cannot be captured by the other telescopes. And then, is it possible to obtain such a kind of information by enhancing the quality of the Hubble images?
Actually, I'm not an expert in astronomy, but I admit that there might be some still. Yeah, I think Professor Chi can. He's also author of our project.
Yeah, that's your astronomy question. I'm one of the astronomers sitting here. So first of all, James Webb Telescope is infrared telescope. HST telescope is an optical telescope. So they don't actually observe the same spectrum. So if you have that technique, we can enhance HST to match the quality from the JWST. So it has a unique advantage. And the second question is very interesting one. We want to even improve the resolution of JWST. JWST is the best telescope in the world, but we need to have a bigger telescope. That will be only possible probably 10 or 20 years from now. But with the technique that we develop, we can apply that technique to JWST to enhance its resolution even better than the current resolution of the JWST.
Thank you. Okay, so if you don't have any questions, so thank you for your insightful presentation once again, and please give him a big round of applause once again. Professor Young-woo Lee from Hanyang University will deliver a talk, and the title is Semi-supervised learning using weighted soft protein technique for open fault detection in power distribution network. So please welcome him a big round of applause.
Thank you for introduction. My name is Young Lee. I'm working for Hanyang University, Erica. So today I will deliver a presentation on the topic of deep neural network model based on effective feature selection for power fault system. So my research, this is just my one paper's research topic. So this research is focused on the AI application for fault detection. This research was supported by Korea Electric Power Corporation. So A few days, years, this project will terminate, but I will introduce this research topic in here. So let's start my presentation. So this is my today's presentation outline. First, I will introduce my system for power fault detection, and then we make the test grid simulation by MATLAB. So because of we need to obtain the new data from the test grid. So, and the next section, we developed two algorithms, purpose algorithms. One is the feature selection algorithms, another is the relabeling algorithms. And finally, I will introduce my simulation result with 4 different cases. First, this is introduction. There are many faults in the power system. These faults cause a violation of power system stability. But there are major 2 faults in power system. One fault is open fault, another fault is ground fault. But open fault is more difficult to detect in power system by monitoring. So my research focused on the open fault detection in power system. So in this work, there are 2 major issues. One is the most data from the measurement has unraveled. And another issue is what is the important information during the many monitoring index. So to handle these 2 problems, we propose 2 algorithms in this work. So to utilize the unraveled data, the semi-supervised learning is adapted to train the classifier. This is the test grid system. My laboratory and Capco made this 3 feeder system. Each feeder has different load and distribute generation and the real remote terminal unit. The RTU is the measurement equipment. So in this system, we have 10 different fault type and 10 different fault location and 30 measurement point. So totally we have 1,100 data point. So this is the fault cases. From this test grid, we get 1,100 data, and we have also 18 independent variables. These independent variables is electrical characteristic, so such as impedance and voltage, current and sequence, and the angles between the voltage and current. So to assign the label for the binary classification, the binary classification means the open fault or not. So 7 types open fault were considered as an open fault. In the next page, we have the 10 different fault cases, the 7 open fault, the different open fault case, and later 3 is the ground fault case. So we used these 10 cases to detect the fault. And this is a methodology. Before 2 proposed algorithms, we have a subset from the test grid data. So total number of combination by selecting S items from 18 independent variables. So this is defined as capital S. So total number of subset from the grid data, so equal to the equation 1. This is an example. So this is my first algorithms. This is done index-based effective feature subset selection. So as I mentioned earlier, it is important to identify the effective feature for open fault. So in our previous pages, we have 18 independent variables, but we choose some 3 to 5 effective features during them. So to train the multiple classifier, it is necessary to select effective feature subset. So by using this equation 2, the done index value is obtained. So these subsets can be considered as input to the proposed algorithms. During this procedure, we have the effective subset. So in this work, we choose 3 effective subset. But sometimes some different distribution power networks, we choose 4 or 5 effective subsets to detect the power port. After that, we also developed the second algorithms named it weighting voting ensemble based on Dunn index. So this algorithms was developed to enhance the accuracy using the effective feature set. So as I mentioned earlier, we have a lot of unreliable data from test grid. The realistic, for the total data set, almost 30 to 40 data are unlabeled. So it is a serious problem. So we define the unlabeled data XU and labeled data XL in this equation 3. After that, we can develop this weighted voting method, and the fluence of the specific subset with high clustering quality increased on the prediction result by using this procedure. So by this defining the YP matrix, after that we can finally obtain the matrix P using the YP and W matrix, putting weighted vector W and classification result. So finally, using this data selection from the input P matrix, we can obtain the 2 labeled, nearly labeled data and nearly unlabeled data. From this procedure, nearly labeled data can be considered as another input to the training system. So we have the original labeled data and the nearly labeled data are merged in the update rule. After that, we can explain the total block diagram of the proposed method in this figure 6. So as you can see, the XL is the previous labeled data. This is the training steps input, and like this prediction steps, we use the equation 4, 5, 6, so we can obtain the XNL new labeled data. This is goes to the update rule of the training step. Surely before this step, by designing my first algorithms, we choose the effective feature selection from the 18 independent variables. After that, this is a second phase. So this is the last simulation result. We have the 4 different cases. The first case is our first algorithm and the second proposed algorithms. In case 2, we have different soft voting ensemble method, and case 3 has random data set method, and case 4 is PCA method. To confirm our performance, we developed a new index. The R is designed by the LP and NP. LP is the number of the pseudo label that match the actual labels. Our data is simulation data, so actually we have the accurate information of the label, but some data's label will be removed, and this unlabeled data will be prediction steps in my previous page. So we can compare the actual label and the prediction relabeled data. So MP is the total number of the instance in the pseudo labeled data set P. So by using these 2 LP and NP index, we can calculate the new performance index R. So this is the first performance of the relabeling. So the purpose method was found to be more effective when using the small label data set. And the proposed weighted voting method improved performance compared to the previous case 2 soft voting method. So we changing the number of data, library data, almost a range of the number of library data. So we have more improved performance in case one proposed method. This is the relabeling data in phase one, and the next phase, the figure A show the validation accuracy performance. So like this previous page, this page show the accuracy. The accuracy means the effective feature selection performance. So our proposed effective feature selection method type can help raise the accuracy. So the proposed weighting voting ensemble also show the improved accuracy compared to the other case 2, 3, 4 method. So this is our simulation result in the sense of validation accuracy and relabeling performance. So this is my conclusion. So to copy the reg of training data, the modified version of semi-supervised learning was proposed. In our works, we have labeled data and unlabeled data. So we proposed like these SSL algorithms. And we also developed two different algorithms. One is the effective feature selection algorithms. Another is the voting algorithms. So by using these two proposed algorithms, we can raise our accuracy to train the model, and we choose the effective feature in power system for the power system fault. So this is our major contribution of this talk. So this is the end of my presentation, and thank you for sharing your valuable time.
Okay, so thank you for your great talk. So any question from audience? Okay, so let me ask you a very basic question. I'm not so familiar with the research field. So what is the data format for, I mean, in the power distribution network? This is 1D signal or the 2D type of the image or the 3D? Or that's my first
Yeah,
question.
just one-dimensional data, and this is the electrical signal. So ampere and voltage, like this number of the real number. Yeah.
The reason why I'm asking this question is that this data is kind of the 1D data, but why you are using the convolution layer? I mean, which is tailored for the 2D data processing.
Yeah. As you know, 2D data usually can be accepted, but in that time we the Capco required one-dimensional data to analyze this fault case. So we just use the one-dimensional data.
So any question from audience? Okay, so let me ask you one more question, and finally. So you mentioned here open port detection, not just the port detection. It reminded me of open vocabulary segmentation kind of thing in computer vision. So do you have any specific reason why you are using open for this definition?
You mean the definition of the open fault compared to the other fault?
Right.
The major fault is open fault and the ground fault. Open fault means this connection, the cable in the power system, and for this cable cannot be contact any other conductor and the ground. So in this state, the open fault. Yeah.
This open is a little bit different from what it's saying in
Yeah.
Okay. So do you have any questions for this talk? So if you don't have, thank you for your insightful presentation once again, and please give him a big round of applause once again.
Thank you.